hanging out. If I don't get to see each of you before you leave, I know some people have flights they have to catch. Thank you for coming. I'll be in touch with you, soliciting your feedback about the workshop and if you think we should do it again and what you think we should do. We just invite all the same people to give the same talks. That would be the most isomorphic possible thing. Or we could seek something completely different, or we could try to get some overlap. Some combination of new things and some combination of updates. So, do that. We're very happy to introduce Vladimir Markovic, who we just hired here. So I feel very lucky. An expert in various things, mainly I think of particular theory, extremal maps, and hyperbolic geometry. I got a little bit lazy towards the end here, so instead I think I'll just read something I found that was pre-prepared as a citation for the Whitehead Prize. So Dr. Vladimir Markovic is awarded the Whitehead Prize for his work on infinite-dimensional Teichmuller spaces. I mentioned that already. Markovic with his colleagues has resolved a number of outstanding open questions, starting in his thesis with a 60-year-old problem about extremal quasi-conformal mappings of regions of infinite topological type, and including the extension to the infinite-dimensional case of Roydon's famous 1971 theorem that biholomorphic maps between Teichmuller spaces of finite-type surfaces are geometric. This is written for mathematicians. Since arriving at Warwick in 2000, from where we stole him, Markovic has been an inspirational collaborator, much valued for his brilliant insight. Another outstanding conjecture which he resolved in the negative with David Epstein is the K=2 conjecture, following a similar answer for the equivariant case with Martin also. Most recently, he and Epstein have laid rest to Dennis Sullivan's dream problem about quasi-conformal disk homomorphisms and their quasi-symmetric boundary values. Well, thanks. Very glad to hear what you have to say.
Thank you for coming. It's early. Okay. So I'll be talking about...
You're in Warwick, it's in the afternoon.
So I'd like to talk about something that I wrote on before and we'll sometimes think about that. There are some even recent results I was involved with the project. Anyway, so I'll kind of tell you a little story. That's really how I think about it. Okay. So first of all, one classical thing in geometric function theory is studying the Riemann map and, of course, its derivatives. So I kind of formulated roughly. You can see what kind of one line of investigations. You want to kind of study the derivatives of the Riemann map, and in this case, you think of the Riemann map as being from the domain, simply connect to the domain that is not equal to the entire plane onto the unit disk, that map by F, and then you want to estimate the derivative of this mapping. So for point Z, here you have point F of Z. You want to estimate the derivative of F at point Z in terms of the distance between Z and the boundary of the domain omega. So once these kind of things, once you look into that, well, these estimates are known. They're known as the curve estimate. I'm not going to claim them. Instead, I was going to formulate two other problems that are just similar in flavor. This is just kind of one basic question. These are kind of similar. One is to, if you have a little disk in omega, disk of radius rho, you want to estimate its harmonic measure, which will come back to that, which is omega of d rho, in the terms of the radius rho. And another question is that you can integrate the derivative of f, take some power, and see for which values of p this interval converges. To put that in some perspective, if you take the power of p to be equal to 2, then this interval of course converges, and it's equal to the area of the unit disk, because that's just the f prime squared is just the Jacobian of this mapping. So if I change the variable formula, we at least know that this exists when p is equal to 2. I will later on tell you what's known and what's not known about just kind of, and you can easily come up with cases that this integral will diverge for large values of p. Just to give you a little hint about that, take the mapping from the upper half plane into the slit region. So take the mapping f of z. That map goes the other way now. It goes from the upper half plane to the region f of z equals z squared. So you can see that this is 0 now. Now when you look at the inverse map, that map, the derivative of it would be 1 over the square root. So if point omega w is here, you would be integrating something like 1 over 2 square root of omega absolute value to the power p over the complex plane. This will diverge for values of p equal to 4 and more. But it would converge to values of p less than 4. So these are kind of the basic examples and the ones that motivate this discussion, in fact. Okay. So the Kerber domain, if it's not clear. Of course, here I use, instead of the unit disk, the upper half plane. Nevertheless, it's a local issue around one point. So once you transport that by a Mobius map to the unit disk, it makes really no difference. So this is the picture I produced, so you can kind of see. But there is something extra on it. So you have omega is this simply connected region, and you have the Riemann mapping onto the unit disk. So now the way, kind of one way to approach these problems, of course, this problem has been studied for perhaps 100 years now, starting with Kerber, and really he was the first one, and Bloch, and people like that. And then, but of course, it's a huge theory. But in particular, there is another point of view that recently emerged a few years ago, or maybe 5, 7 years ago. Another point of view. Well, actually, maybe we should say maybe 20 years ago, Pearson Thurston. But then it was put into context of this analytical question more recently. So once you have a simply connected domain, you can, as we heard many times in this conference, you can take all the disks inside your domain and take the hemispheres above them and take the union of all these things, and the surface of that, the boundary surface of that lives in the hyperbolic tree space is what's called the convex hull bound. An alternative construction is to take the boundary of your region, take its convex hull in the hyperbolic tree space. Itself, that will be a tridimensional object, and it will have two boundary components inside. I mean, they will have the same boundary on the boundary of the tree space, but inside the tree space, you have two boundary components, which are surfaces. And you take the one that's closer to your domain omega, and that's called the convex hull boundary that we're in. So I say the convex hull boundary, that's the object I'm referring to. Or I just call it dome. In fact, that invented by Almari because in Minneapolis, the football stadium, the Metrodome. It looks like a dome, really. Well, and maybe other football stadiums in this country. So it's kind of there are more similarities to that structure than I'm communicating here. Between
it has pleats, like.
Yeah, it has actually pleated. It has bending lines in it.
I always think it looks like those worms in Dune.
I used to live, and my apartment was looking over that, so I remember these bending lines and thinking about that a long 7 years ago. Okay. Anyway, so this is the story. So you have this classical Riemann map, but you can do something else. You can take this convex hull and then look at maps H that go from omega up to the dome. But these maps are required to extend to the boundary continuously and keep the boundary fixed point-wise. So they're identical on the boundary. Okay? Now, the iota map is, so the dome, which I will show you more kind of better picture of with the real computer images. Nevertheless, as we heard already, the dome is, at least in special cases that are dense among all the cases, could be thought as a locally flat surfaces in geohyperbolic space that meet at the geodesics, and then there is a bending angle. So the two geodesic planes meet at an angle, and that's how the dome looks like. So And as such, by the iota map, developing map is isometric to the standard unit disk. So this is a known as theorem of Thurston, but I mean, similar theorem for Euclidean has been proved by Alexander many years ago in R3. So that's certainly all the same thing, really, just in the quality case. So then you go back to the iota map, and then the map G, eventually that maps the unit disk onto itself is induced so that you get the representation of the Riemann map with G composed by I composed by H. So for now, the only requirement here is that, and I will say very soon why, is that H extends to the identity to the boundary. It can be, well, it's a continuous map certainly, but it may or may not have other properties as well. Okay, so that's the convex hull boundary. So let's see some example of a convex hull. I don't know if you can see that, but in the case when a domain, omega, is a union of round disks, now the convex hull boundary would have quite a simple look. You would just take the hemispheres like this, just as done in this picture with 4 disks. So it's written down. And then the convex hull will be union of these hemispheres. Well, you have discard pieces of the hemispheres that are below. It's kind of self-explanatory. There's really no point in me saying more about it here. Anyway, so on the other hand, it's not difficult to approximate every region, every domain by those that are by domains that are union of round disks in this case. So therefore, in a certain sense, well, in this sense, exact sense of approximation, if you understand this case well, you can prove many various things for the general case. Well, those that can be obtained in the limit. And in this talk, the quantities we'll discuss will be like that. So you can always just study them in this case. Well, that doesn't really make them simpler to study. It just makes sometimes, once you start thinking about these convex hull boundaries, it is somebody said that it's kind of difficult maybe to visualize what's this convex hull, and I found it actually too. So, this is kind of maybe the good first example to look at least from my point of view. So, while I'm here, I should say, I won't remind you what's a bending line. I'm not sure people will talk about it, but so in this case, where there is a line here, it's a geodesic in the hyperbolic tree space, where the two hyperplanes intersect, two hemispheres. That's called the bending line, and the angle that they meet, or the angle that two planes meet, is called the bending angle. So, just kind of to make sure that's clear. Okay. So now let's go back to this map H. So, keep this should be kept in mind, this diagram, because it's basically a core for understanding. So you have Riemann map H, I, and G.
Did you actually say what H was?
No, I just told you it's a map of the floor, of omega, which we call the floor. By the way, results that I will present here, actually, results that are not named are done by me in cooperation with David Epstein and Al Marden, or one of them, or both of them. So I'm not going to. It's really harder to draw work. Anyway, now we're going to discuss this map page that you asked. Now, first of all, the first thing I would like you to kind of note is that once you, only if you require that H has to be identity on the boundary, that already determines the boundary map for the map G. That's kind of important here. So take omega and its dome. So I have this picture because it's important. Then you go back by the Riemann map here. Then the iota map goes back to the unit disk. And then you have the map G here, and then it goes from omega to dome of omega. Now, and we know that F is H composed by iota composed by G. Now, just the fact that H extends to the identity, to the boundary, implies that the boundary values of G is a map to itself exist. Of course, if G extends to the boundary. But that concept is developed. I'm not going to go into these details, but that will certainly always happen in the case of the frequency. Anyway, on the other hand, there is a special map. So the first map, H, that you should consider, that naturally represents maps from the omega to dome of omega that fix the boundary point phi, is the so-called nearest point attraction, is where you take a point in the dome, in the floor omega, and then take the Hora balls. Now go into the upper half of space, take the Hora balls, and build them until you hit the boundary, until you hit the convex hull boundary. Once you hit it, that will be the image under the map R of Z, which is called the nearest point attraction. The fact that this is a convex hull boundary makes this map well defined, which means that you will hit it at a unique point. So that's a nicely defined map, and it naturally extends to the boundary. And it is essential. It's crucial for this discussion here to understand this map and actually its geometry. What is also important to understand is that this map is not necessarily a homeomorphism, because if you have a bending line here, then the pre-image of this bending line under the nearest point attraction can be an entire crescent embedded in your domain omega. So we will see some figures of that in a minute. But of course, that only if the bending measured at that bending line is atomic. So if there is a definite angle that you bend along the bending line. For example, if your region is smooth, if your boundary curve is smooth, then the nearest point attraction will be a C infinity diffeomorphism. And so the only, when it's not going to be diffeomorphism is when you have corners in the boundaries. Actually, that's where. So it's essentially a technicality that's easily be resolved. In fact, you can choose another map. So before that, this is the basic. This is the first and one of the most important things about this construction. When you compose it by the iota map, and map omega into the disk, this map is Lipschitz with respect to the Euclidean metric. So first of all, you can just ask a question. If you have a simply connected region in the plane, can you find a Lipschitz map of that onto the unit disk? Of course, you can take a constant map, but can you find a Lipschitz map of that onto the unit disk? So the Riemann map won't be like that in general. And this is not to say that that's a really difficult problem. It's not, but this is a natural example of doing it. And I think that it has value from that point of view. On the other hand, if you are worried that R, the nearest point attraction, that latter reserve for the nearest point attraction, if you're worried that that's not a homeomorphism, you can perturb it slightly to get a homeomorphism, and you can essentially up to a constant epsilon that can be actually small preserve all the vital values of the nearest point attraction. So, in particular, you can arrange for a map H here to be a homeomorphism, a quasi-conformal homeomorphism, so that the map G here is a real analytic diffeomorphism of the disk onto itself, so that the corresponding map here, H, composed by I, is a Lipschitz map. Just by a very small, in some sense, arbitrary small perturbation of the map R. Of course, the constants then might depend on that. Okay. And now the final line here is that going back to the Riemann map, you can obviously estimate the derivative of the Riemann map just by understanding the map G. Actually, so you have this point here, omega, and then you have G of omega, and you want to estimate is less than or equal than a constant times the derivative of G of omega. So omega is the corresponding image of Z under the position of these two maps for that. I write the derivative of G. G is not complex analytic, but nevertheless it's they can reasonable norm on it. Call it the derivative. Okay, so now you can essentially ask the following question: can I estimate the derivative of the Riemann map? What do I actually need to know about G to be able to estimate the derivative of the Riemann map? And that's kind of the question. But before that, let's kind of take a little bit of break and let's see some examples. So this is an example of finitely bent region. These are the regions whose convex qualities are just doing in a finitely manner. Canvas used like that, and there are in this case 1, 2, 3, 4 bending lines, and the crescents that are underlined there are actually the pre-images of the nearest point of traction. So these are the pre-images of the bending lines under the nearest point of traction. So in this case, in the cases like this, the nearest point of traction is an isometry. Well, no, let's not use that word. It's a Mobius map from the outside of this crescent. The nearest point of traction is a Mobius map. And on these crescents, it does some collapsing. So that's how you glue these Mobius maps, by these collapsing maps to build up the nearest point of traction. That's just in the finitely bent case. When you pass to the limit, these crescents get equally distributed, and they mix up with this Mobius map to give you your diffeomorphisms. So these are the things actually that you do study in order to understand the Riemann map better, but they were also perhaps independent features sometimes. Anyway, but first of all, I print enough times what's the basic conformal mapping and what's. So whenever I have a mapping, I will denote by K its basic conformal constant, which is just the maximum distortion. Well, it's a distortion. It's the maximum stretching divided by the minimal stretching on the tangent level. And so that's just the usual K. Now, whenever you have a domain, a given domain, you can look at all the maps from the omega to the dome of omega that are identity on the boundary. And then you can ask, what is their basic conformal constant K? To make that precise, you wonder, what's exactly a basic conformal constant here? Because this thing here, what's actually the complex structure we are looking at, really what you should look at is into the map G, because I is really, in our world, the conformal map here. So K of G, well, is actually equal to K of H. So you can define K of H by setting it to be K of G. So K of G is a map doing this onto itself, and therefore you know what's flotation. Now you can define this number. So one thing I'm missing here is the infimum. So K of K of omega is the infimum of this K of H, that map omega to dome omega. Okay. So that's just the infimum of that. Now you take K is the supremum over all regions omega. And L is the following. Is L of R is the nearest point of traction for a given domain. And now L of R is the Lipschitz constant of the nearest point of traction, but in the following sense. So this is the different Lipschitz metric. Now you have the natural hyperbolic metric on the domain omega always, that's just obtained by the pullback by the Riemann map of the standard one of the unit disk. On the other hand, the convex hull boundary is a surface in R3, and it has its intrinsic metric, which is, in fact, as now by this theorem of Thurston, since it's a metric of the unit disk, we know that that's also a hyperbolic metric. So, because R goes from here to here, you simply can talk about R being Lipschitz with respect to the corresponding hyperbolic metrics. And whenever you refer to the Lipschitz constant of the nearest point of traction, that's what it means. It means Lipschitz with respect to the corresponding hyperbolic metrics on omega and the dome of omega. And then you look, so for a given domain, that's a given number. because there is only one nearest construction. But then L would be really, again, the supremum of all L of R's when R. So maybe it's not necessary, but anyway, it's the supremum of all L of R's. Omega varies to all the possible simply connected regions like that. So of course, when you define these numbers, you don't know whether they, because you define something to supremum, you don't know whether they exist in the sense that whether they are finite. So the first theorem in this kind of subject was something that, well, it says that K and L are well defined, and in particular gives you some estimate, basic estimates on K and L. So it was proved that K is less than 70 first time, and that L is no bigger than 4. First of all, it should be said that this was just used by Thurston, the fact that K exists for his application, three manifolds, and I decided not to kind of sketch what's the relation of these three manifolds, because that's what take us, it's unnecessary. This is also equally, this is more physical in some sense, but this is in some sense intrinsically related to three manifolds, because you want to compare the structure at infinity and structure of the convex, of the boundary of the convex core of a three manifold. So that's where this constant K comes in, and he used that constant exists and it's universal. This is a little bit more general theorem because it tells you that you don't need the group action of domain omega to get that. So, and the theorem was first proved by Sullivan, which really, he just said it was true. That was kind of a proof. And yeah, that's a short paper. I never read, but really, because, I mean, there were no constants.
I think he summarized it for us correctly.
Yeah. Well, he attributed that.
Take several paragraphs and say it's true.
Yeah. He said this is a theorem of Thurston. Yeah. So, what is technically difficult is to get any kind of estimate, numeric real estimate, not their existing estimate. So, in fact, this theorem is really not difficult. Once you know it's true, and once you kind of recognize that something like that exists, it's relatively easy to prove that constants exist. In fact, we have a recent paper which applies to multiply connected regions, so to all regions. You can kind of easily say when the constants will exist, but what's not easy to do is to get exact estimates. And from Thurston's point of view, where he used just the existence of constants, that made it really plays no role in his. And of course, they were not interested in constants. Although he did ask, actually, he conjectured what's the value of the constant. We'll come to that later. Nevertheless, these numbers became important later. So the first proof that K is less than 70 was more than 100 pages by Efton and Martin. And that's a very technically complicated paper. Very hard to read as well. But nevertheless, that was the first kind of estimate that existed.
This is a side note, can I insert to your talk? The fact is 100 pages, and I couldn't penetrate beyond page 14 or 15. Was the reason why I really got seriously more into the subject, because I decided I needed to find a proof which I could understand. So, hard technical papers are useful sometimes.
But nevertheless, their proof that L is less than 4 was very short. And it follows from basic Kobe estimates. Okay, so now we know that these constants exist. So let's see how that relates to the conformal matrix. First of all, going back to that little disk here, radius rho, we take its pre-image here, typically would be disconnected. The first thing you can do to prove is that harmonic measure of a disk of radius rho is less or equal than a constant times rho to the power 1 over L, where L is the richest constant for the nearest point structure. So the way this is, such a force estimate is known for rho, well, in this case, that would agree with L equal to 2. And then that's called the Beurling estimate of the harmonic measure. It's a classical, very nice result. But I'll just tell you how that's being proved by using this diagram. Is that you just take this disk, because it has radius rho, because this map is Lipschitz, you go onto here, you look at the image of it here, and just take the entire thing, the entire interval, where the image of the pre-disk, of this disk comes in. Now, all you need to estimate is where is this being mapped by the map G. So in fact, if G is Holder with the exponent 1/2, you would be fine. And the fact that G is Holder with exponent 1/2 does indeed easily follow from the fact that H or nearest construction is Lipschitz with the exponent 2. That's just easy hyperbolic geometry. So this is really elementary to see that the estimates of the harmonic measure of this can be estimated like this in terms of the constant L. What's more involved is, in fact, these ideas were started with Chris Bishop. He actually first showed me this thing, and this is the first thing I showed you. I came up with that like 3 days ago, or 2 days before making the abstract for the talk. Just kind of to say something, to kind of try more to communicate what you're trying to do here. So he showed that this integral here, that we have already mentioned, converges for p less than 2k over k plus 1, which is, and that essentially was done in the same way up to the point where you again look at the map H composed by an iota. That's a Lipschitz map. And now to estimate the derivative there, you need to estimate the derivative of that map G. Now, on the other hand, there is a beautiful and very important theorem of Stella that says that tells you when, to which power you can integrate the derivatives of quasi-conformal maps so that the integral would converge. And he gave the best constant in terms of the dilatation, the dilatation k of that quasi-conformal mapping, and that's where these numbers were read from. So that's certainly, and the proof of that, there are experts on the proof of that theorem here. But the proof nevertheless relies on applying applied holomorphic motions and Harder principle, and I'll come back to that a bit later. So think of holomorphic maps and Harder principles. Okay, so these are the connections. So between this analytical questions and this kind of geometry, hyperbolic geometry. So, in fact, it was conjecture, and that's certainly a now famous Brennan conjecture. This integral converges for the values bigger than 4 over 3 and less than 4. I don't know if it's bigger or equal than 4 over 3. I forget. It might be. That bound has certainly been proved by Gehring and somebody else. I forget exactly who it was now. But the bound, certainly p cannot be bigger than 4 or 4 because we saw this Kuba example. And the question is whether it can be done up to the constant 4. I really don't know. In the recent years, there were many partial results improving the upper bound for p. It's sort of close to 4. It's 3.7 or 3.5. I really don't know who has the late. I kind of was not following this maybe in the last 5 years. But anyway, so there are. This is people really think about that. Anyway. Going back to so the corresponding conjectures in the hyperbolic, in the convex whole boundary setup are that the constant k is equal to the constant L and the chord are equal to 2. Thurston incredibly observed. He made a connection with the Kuba slit region that we discussed. It comes from the map Z square, and he observed that the k for that particular region will be 2. And he made a connection with the classical function theory, saying that that should be really the best. That should be the extremal case, and the constant case should be not more than 2. And that he wrote actually in that paper where he proves his version of the factorization conjecture for 3 manifolds, where he uses the theorem just in the existence of constants. The conjecture L equals 2. I think that came slightly later by David Epstein. So let me tell you a few things immediately. One thing we proved is that, and that will be kind of the first thing, is that if omega is a Euclidean convex region, then k of every such region is not bigger than 2. In fact, I will show you some convex skulls of convex regions on the next slide, but I will just tell you roughly why is that the case. So convex regions, we can just think of convex polygons in the plane. Now their convex skulls are essentially built up like this. So it's a union of wedges like this, and then they all meet in the flat piece. So it's a piece of the hyperplane in the tree space. So they kind of meet. So you can actually now build up the map from omega, in this case the dome of omega, by taking the map just for the wedges like this, where the convex hull will go like that. And you can just take the maps from the floor to dome in these cases and then piece them around this desk. And then it just so happens that you can compute, in fact you just can take the nearest point attraction and that would be good enough. The nearest point attraction would be actually two quasi-conformal in this case. So, you see the nearest point attraction is not homeomorphism when you bend more than, so when it's anti-convex, when you have a spike in the boundary of the domain. When it's convex like this, then it's a nice homeomorphism. And in fact, it's quasi-conformal, constant not bigger than 2. So that's a geometric kind of proof of. And of course, then you pass to the limit. There is some discussion there that you can pass to the limit of all convex domains. But so the proof here, this is kind of the first thing that I realized. I thought this conjecture might be true because it nicely works here. You can kind of write down things and so on. On the other hand, one thing that does work for all domains is the Lipschitz constant, and that is actually 2. There were estimates before that. I think Canary had some estimates that were in between 4 and 2, and Bishop had an estimate. Somebody else might have, I don't remember. But nevertheless, it can be proved that L is equal to 2, and it's a maximum principle proof. You just you take this finitely bent region, pull the metric back, and then compare it by maximum principle, and there are a number of cases. But kind of harmonic analysis does it. I mean, estimate L equal 4 just comes from the Kerba estimates, and this is a little bit more evolved. Anyway, so this convex region and a wedge, and it's convex hull, and there's some discussion of how that goes. So we have a dome, and then all these drawings that I take from my papers were made by David Epstein, so I don't know how to make it. And we've done a lot of geometry, I mean, sort of differential geometry in some sense of this kind of work, this one is hull boundary. And there are pictures to show for it. Anyway, so now I'll just tell you, I raised some questions and I gave some answers, and the question that's not been answered at the moment is that what happens with the constant K, and we will soon see that. But to do that, one way of doing it is to try to make a connection with something else in the theory. If you're not familiar with binding groups and stuff like that, you may as well ignore this. This is really more the case that Thurston was interested in. So if you have this domain omega, this domain might be invariant under a Kleinian group, say like once punctuator's group or some other. And then you can look, then the same would be not, of course, true for the dome. And the dome would be invariant under the same group. And by just kind of saying it in one sentence, you have the invariant version of all these things. In particular, you can define the invariant quasi-conformal constant K just by minimizing over maps from omega to dome of omega that preserve, that commute with the action of the group. So that would be the equivariant version of the constant K. On the other hand, the constant L is naturally equivariant. The nearest point attraction does commute. And just if somebody, so Thurston has a perhaps not so well-known work on minimizing Lipschitz constant in a given homotopy class. He showed that if you have a map between two closed Riemann surfaces, homotopy class of a homeomorphism, you can find the minimal Lipschitz constant, and it's enough just to look at the quotient, the ratio between the length of geodesic in the corresponding homotopy class. That's actually equal to the minimal Lipschitz constant. And he constructed these extremal maps that actually realize this Lipschitz constant. And these nearest point attraction are actually these. I actually observed that, and one can try to prove that. These nearest point interactions are actually the extremal. They minimize the Lipschitz constant first when they come to the class. Anyway.
That's just in the generic case.
Yeah, just, well, that's another case. One can extend Kapster's theorem to other cases. Just, I don't know if that's interesting. Maybe it, well, that could be interesting. Anyway. Okay, so, but in particular, so this, let's go back to this bending, the structure of the dome. The dome is made of, well, the dome is uniquely determined by a measured lamination of the unit disk. Now this is a discrete one. It has several geodesics, and then you put a measure on it. In this case, this is the atomic measure. So if you have a geodesic lamination, a measured lamination is when you put a measure on the interval transverse to the lamination. And that's a positive measure. And then that's called the measured lamination. But if you have a case like this, then the dome will just arise. So you just take the unit disk and just bend at this geodesic in the tree space. First of all, blow up this to a hemisphere in the tree space. Think of it in everything geometrically hemisphere in the tree space, and then start from a geodesic. So we'll go like this. This will be the disk originally, and now the geodesic lamination, the measured lamination, just looks like this. And now you have the measure of these lines, and then just keep bending, go piece by piece and bend in the hyperbolic tree space. Bending is nothing else but a Mobius map that preserves this geodesic and fixes one plane to be identical, and the other plane you just rotate along the geodesic by a Mobius map for the given angle, and that's how you obtain this dome. And that's in the finitely bent case, and the general case is just kind of limited to this naturally. Anyway, one thing that has been, I don't know where you can start, I've seen it first time in David Epstein's papers, is that you can multiply this number, this measure by a complex number, whose measuring part is not positive. And then, and people actually have been mentioning this at this conference. Instead of just bending, you can also earthquake along the bending lines. So as such, you will produce a family of surfaces in our tree that depend on this complex parameter. That's called quake bending, or modern terminology, complex earthquake. So this map is naturally defined. Actually, you can easily define it just to get the surface. You can easily define it for every t. T that need not be. It can be any complex number. But to have any hope of doing what's below that, you first want to restrict yourself to the case where the measuring part t is of z. Okay, this should be this. Yeah, no, it's okay. T is non-negative. In fact, in that case, when the measuring part of t is non-negative, then you can define a natural mapping just by. So once you bend, you arrive at this dome, and then you take the nearest point extraction, and then the iota map back to the unit disk. And then remember, the boundary value of the map G here does not depend really on the choice of the map here, as long as it fits the boundary. And that gives you, so as a result of this, bottom line is that you get a mapping from the S1 to itself, which is element of the Teichner space. The fact that it is in the Teichner space follows from the fact that these universal constants exist. So you get an actual, okay, this should be explained more, we don't have time, this is more or less informal. You get a natural mapping from the upper half plane into the universal Teichner space, or the Teichner space with the unit disk.
The Teichner space of the disk is the space of homeomorphisms of the circles.
Yes, Teichner space of the disk is just the space of quasi-conformal homeomorphisms, normalized or not made with. And there is an actual Teichner metric, but itself is a complex manifold modeled on a Banach space that says isomorphic little L infinity. Now, it's a theorem of McClellan, at least in the group invariant case, that can, I think, be extended as the general case for our purposes, is that you can extend analytically this map to some portion of the lower half plane. And then eventually the domain of this mapping will be called D, and then we get the homomorphic map into the Eichner space. Anyway, just to kind of speed it up a little bit. This is where the first example, this counterexample to this K conjecture comes from. You can look at diagonal space of one function torus groups, and then I'll just make a little sketch here. So this is the upper half plane, and then this is the space of T's. So that when you bend your surface for parameter T in this bit, your split surface that arises is embedded. In fact, it's a convex hull boundary of a simply connected region. If you bend more, your surface will start intersecting itself and there will be no more simply connected region. And symmetrically to that, the lower half plane, you get is exactly where this map extends analytically to a map into the diagonal space. That's more or less the tautology. But anyway, that's we found discussed that and he observed that. So now you get, in the case of the puncture torus, this map F from this domain onto the diagonal space of the torus, which is the same as the unit disk. By dimension count, this map is bihomomorphic and it's isometry with respect to the diagonal and the corresponding hyperbolic metric on this region. So to estimate the constant K, you really need to estimate, this was the origin of the bending. The bending corresponds just to the T being purely imaginary number. So you just go above it to the line here. So this T naught corresponds to your dome and the hyperbolic distance between 0 and T naught into the domain D is actually equal to your K of the corresponding domain omega. That can easily be proved. Of course, I cannot take me 2 hours to explain exactly why is that. But nevertheless, this is one comment that can be made. And now, I was looking at this picture. This is the McMahon's picture, or a version of it, anyways.
Dave Wright.
It's David Wright's picture, yes. But I saw it first time in McMahon's paper. I was looking at it for hours one night, and then I realized that you see that this, if you add a line like that so that everything will be contained in it, then and in this point here was the minimal point, then I would get that my hyperbolic distance between this point and this point must be bigger than 2. Just as a corollary of the fact that this is a wiggly curve, it's not a straight line, which is not difficult to prove. McMahon proved it numerically. I can prove it 10 ways, but it's actually never formally proved in anything.
I think the minimum is the golden mean.
Exactly.
Yeah.
It is indeed, yes. That's what I learned from McMahon. Yeah, the minimum point is at the golden mean. So for that point, and for the nearby points, you get this counterexample. And that's how they look like. That's another picture drawn by David Wright. Yeah. So we have, again, Nancy Chris, so he should be placed at his other work. Yeah, this David Epstein wrote these comments. So he says, limits n must get countermeasure 2 for that golden mean, and then that's why this kind of thing becomes blank. So this is the one it says here. So that corresponds to this point here, or some nearby point. There are very recent results by Charles Matthews and Komori, or maybe somebody else, they find more of these examples and much lower. I don't know. I didn't understand that. It's quite computational. they should have actually.
So just in case anyone missed it, the point of this was that Thurston's conjecture is false.
Yeah.
But you said equivariant in
Yes.
slide now.
So that means that you only have to take quasi-conformal maps that preserve, that commute with the group.
Yeah.
If you take those that don't commute with the group, that constant will be lower.
Yeah.
That's a theorem of McMullen.
Oh, it is low.
It is lower.
Wow.
So that's also McMullen's proof of the Krafts conjecture. I mean, I actually can prove that fact much. McMullen proved more than that, but that fact itself is not very. That constant is always strictly lower. It is known that it's always that you can't get it. It's never equal.
So we still don't have the counterexample for cadences too.
Well, we do.
Okay.
Spherical logarithmic spiral. So I'll go back to this. Let me show you some logarithmic spirals first. So you have these are for various values to see logarithmic spirals. And then again, it's a maximal circle. The maximal circle is something you need to know to determine the convex hull boundary. Turns out it's really hard to compute these maximal circles and their radii, which are knowing just the constant for the spiral are beyond my understanding why that's so complicated. The first numbers we get, they left and got, they were like 70,000 characters. I really don't understand why that.
I mean, it wasn't a rational.
Now, far from it. Anyway, then this is how the dome. Now the dome looks like the corresponding convex hull boundary. Looks like it's a snail. Draw some lines there. And then now this you can compute. So I'm not going to say anything about that, but this uses theory of extremal quasi-conformal maps. You actually can compute this case number projected with the conjecture. You can compute them here for the spirals, and there are other reasons why to look at the spirals. You ask me, I can briefly answer why. Anyway, this is you can compute explicitly the dilatation k with respect to c. Just an experiment, and one, yeah. Then you just see that for a certain value of c, this k constant becomes bigger than 2, and it just so the graph is like this is c. Yeah, I have this kind of. This is the axis c, and this is the constant k for that corresponding region.
What was the C in the function again? How tightly the
C is I'll go back to that. It's just in this logarithmic spiral, you write it, x goes to e to the power x times c plus I. So omega is the complement of the logarithmic spiral, obviously. And then the theorem says that there exists c less than 1, so that c is bigger than c naught less than infinity, and then you always have is bigger than 2. And the maximum is roughly there. For c close to 1, you get 2.11, and that's I think that. So it's not really much bigger than 2, it's just for some reason it goes above. Anyway, I think I should stop here. I'm sure that I broke my. So I'll stop here.
Okay, well, thank you very much. Are there questions?
Why did he say that alone is
He observed that, yeah, I don't know.
He had case of EQ, I forget, he just meant equivariant. For that example, you have this group acting in group, so I guess he wanted an H which commuted with the group.
Yes. That's what you've seen as a map between rectangular space or function source. That's why. But you can conclude the equivariant. Of course, the equivariant follows from the non-equivariant. That's when it's always bigger. The only thing is now to approximate equivariant cases by those coming from snail, but you can do that.
So what's happening in the snail? I mean, I guess as you wind into these curlicues.
So I'll say why is loop into snail.
Yeah.
Just briefly. So I'll just take the standard. So what's the one-dimensional version of bending? You take the unit disk. The unit disk plays the role of the hyperbolic tree space. You take the interval 0, 1 and put some points here. Put atomic measures on these points. And now map these subsequent intervals into geodesic pieces and just bend along these points. So there are standard basic theorems in differential geometry tells you that if a curvature of a curve, well, the curve should be smooth nevertheless. If the curvature is small enough, your curve is embedded. And in this case, you can look this kind of curvature. You can look amount of bending per length, per given length. Say here in the hyperbolic length. So if that ratio is small enough, this curve will be embedded. So I was thinking, when thinking of these problems, I was thinking in H3, you want to kind of look into similar thing. You know, get some quantity that would guarantee the completed surface is embedded. So you can look at the. So now going back to the three-dimensional case, when you have this lamination, and when you get your embedding by the completed surface after bending along it, you can look at the transverse line and the corresponding line here. And you can now again measure the bending when the line hits. And the bottom line, theorems that are true in the unit disk are false here. You can, I mean, same kind of estimates that you would expect that if something is less than, if the curvature is less than 1, I think it's in the unit disk, then you're embedded. Things like that fall apart. They are not true, and the spirals, and you can compute that in the spirals more easily. And that's what in the spirals, you see that they fall. They're not true for the spirals. They're true for some spirals, but not for all of them. And that's why that could be a candidate to try to get this. And that turned out to be the case.
Well, from a purely technical point of view, it's convenient for doing a computation if your domain is homogeneous under a group.
Absolutely.
And the spirals you dilate and rotate. I mean, the next easiest thing would be like a strip, but that's too simple.
Yeah.
And so the spiral
That's
is the
convex.
next.
That's convex.
Yeah.
Strip is convex, and that's
It's sort of the long-Bernoulli spiral is the simplest non-convex, but still invariant under a simple one-parameter
But
group.
you're trying to show that no H is good, so
Yeah.
how are you going to get a hold of that? Can you show if there's some H?
Yes,
Well,
that's
philosophically, if there was some H, you would average it out over the
Average
group
it.
action,
Yeah.
and then the average of QC map should be better.
That's good.
Okay, that's I see.
So that's a philosophy of Kurzweil, in fact. Once you have these nice groups acting, you take something that's supposed to have the minimal dilatation or so, but then averaging it gives you even smaller one. So your extremal map is indeed just invariant under this one parameter group. But you see, that's because the group is amenable. That's exactly what McMullen. And discovering groups are non-amenable, then this projection has. So the things that are invariant under groups have strictly bigger dilatations than those that are not. So here, the catch is that the one parameter group is amenable. That's why you get that the averaging actually does not increase the constant. So that's really the perspective.
Anything else?
About this mapping iota,
Yeah.
what is the construction in this case?
It will be the same, I think, as in every other. So, I think it's the same map as everybody else talk about. But I will construct its inverse. That's what I like better. You start with the unit disk and take some geodesics on it and put the measures on them. And then, as I said, go to the hyperbolic tree space. Keep track of your geodesics and the measure that's in them. And now just keep bending. You bend along that geodesic.
Was your
Rotate.
question general or specific to the spiral? Or general?
General terms.
Well, the general principle is really like that. You keep bending along your measured lamination until you finish it. That will give you a domain. That will give you the convex hull boundary. And then if you're lucky, that will be actually a dome over a simply connected region.
So you could lose simple connectivity.
Absolutely. That's so let's say that's quantum today. Yeah, you can lose simple connectivity, and you actually should, because this estimate here, I mean, this is the catch. This estimate here, I mentioned that I said, fellas, Astala proved the theorem, his theorem in the same way as this, actually. Except in his case, he used this is the Schwartz principle, estimate on the hyperbolic distance in the domain. Because if you draw this line, you just get the distance. This is exactly log of 2. And then by the inclusion, this will be strictly 0 and 2. So this is the version of the harmonic principle that's being played here. But just to be other to the counterexample. You can get estimates, good estimates on the constant k by the same principle. And that's being done as well. Although the estimates you got for Bishop, I think, has the estimate of 8. K, the best upper estimate for k is something
7.82. 8.
You can use this Schwartz principle to get the estimates of k. But only in the case of the puncture torus do these things agree, the metric, the tachymal metric and the hyperbolic metric. That's only in the case of puncture torus. Then you can actually, you can't get counterexample like this in any other case.
Anything else? Thank you again.